In this video, we're going to look at how we can use the unit circle to solve circular functions. This is the kind of question where you're given the exact value of your circular function, and you have to figure out the possible angles that could achieve that exact value. For those who don't know me, my name is Chris Heinazoni. I've been tutoring for about 2 years now, and I make these videos so that VC students can do the best they can in math methods. With that out of the way, let's get into it. Solving circular functions is always going to be a matter of following this 4-step process. Now, there's a lot of possibilities here, so we're going to start with some of the simpler ones and then work our way up to the more niche examples. The typical circular function question will look something like this. You're given the exact value, the angle is unknown, and there is a domain that is applied to the question. The first step in these scenarios is always to rearrange our equation until we get an exact values expression. And by that, I just mean getting the circular function on one side and an exact value on the other. In this case, we already have this. We have cos on one side and root 2 over 2 on the other. So we're just going to move on to the next step, which is to use substitution if we have a composite function. And that just means when we have anything other than x inside of the brackets. We do have just x in the brackets, so this step is also not required. We will look at how to handle that in example 4. Now we move on to actually finding the solutions, which just means pulling out the unit circle and then looking for every spot on the unit circle where cos is equal to root 2 on 2. In this case, the angles could have been either pi over 4 or 7 pi over 4. Our domain was 0 to 2 pi, and so that's where we stop. We've already figured out everything within one revolution, 0 to 2 pi, of that unit circle. Here we have a circular function that requires rearranging. This just means we want to get the circular function on one side and the exact value on the other. All we do here is multiply by 2. Having done that, we just follow the same steps as before. This is not a composite function, so we move on to the third step, which is to find the angles that correspond to sine becoming root 3 over 2. And when you do that, you're going to figure out that the angles are going to be pi on 3 and 2 pi on 3. Again, our domain was 0 to 2 pi, and so we've figured out all the solutions required. But not all domains are going to be from 0 to 2 pi. In this example, we have negative pi to pi. To begin with, the first 2 steps are already done, so we can move straight on to the third step, which is to actually find those angles. If we were to do one revolution, then we would find the answers 0, pi, and 2 pi. Now, remember, our upper bound is pi, so 2 pi is greater than pi, we're going to ignore that from our answer list. The second issue is that we haven't found any negative angles. The way we do this is by going in the opposite direction, the clockwise direction, and we figure out those angles as well, which in this case is going to pick up the solution negative pi as well. These kinds of questions require a little bit more effort. Now, you might have been taught a different method for solving these kinds of questions, in which case, if that already works for you, then by all means go ahead with that. I just found that a lot of my students struggled with that, and this method appeared to be more consistent. Starting off, we're just going to do a bit of rearranging here. Nothing special, we're just going to put the half to the other side. The next bit is special. This is where we use a substitution, which just means replacing the brackets of our circular function with a single letter. In this case, I'll use u. You'll do this anytime your circular function has anything other than just x in the brackets. The reason why is that all the transformation factors that apply to the x make the domain that's given to us a bit misleading. So my recommendation is to rewrite that domain purely in terms of the new variable so that there's no ambiguity as to how you handle it. We do this by subbing in the x values of our old domain into that u equation to convert them to u values. This will give us a new domain purely in terms of u. From here, we just move on to solving the circular function. In this case, we're looking for where cos is equal to a half. Within one revolution, we can see that our angles could have been either pi over 3 or 5 pi over 3. But our domain is larger than a single revolution. It's larger than just 0 to 2 pi. We handle this situation by repeatedly adding 2 pi to our previous solutions until we get bigger than our upper bound. The reason this works is because adding 2 pi to an answer is the exact same thing as doing an additional revolution. Take pi over 3 for example. If you started at pi over 3 and did a full revolution, it would be at the exact same spot as before, but 2 pi ahead. This is exactly the same thing as just adding 2 pi. We just do this until we exceed our domain. Having done that, we're just going to trim that list. So we're just going to look at that u domain and then cross out any numbers that were larger than our upper bound or smaller than our lower bound. If you have trouble figuring out which fraction is bigger than the other, just make sure to rewrite those fractions purely in terms of the same denominator. That makes it much easier to compare. Having done that, we move on to the last step, which is to get everything back in terms of x again. And the way you do that is replace u with what it originally was. From there, you rearrange to get x on its own. In this case, this means dividing all solutions by 2 and then subtracting pi over 4 from all solutions. The end result of all of this is that you have a set of solutions that fit perfectly in that original x domain, and you don't have to worry about if you found everything. The last two examples are much rarer. In this example, we can solve this via factorization and the null factor law. We just need to get our exact values expression, and we can do that by taking out a common factor of cos. That's actually going to give us two individual expressions using the null factor law, which we then solve individually. Starting with cos equals 0, we go straight to solving those angles, and we figure out that the angle is going to be pi over 2 or 3 pi over 2. And then finally, moving on to cos equals -1, there's only one possibility there, and that's going to be at pi. Sometimes you can simplify things by converting to tan. The thing to look out for here is if your expression contains both sine and cos in it. In this case, if we get the circular functions onto individual sides, we can divide both sides by the cosine. That's going to cancel the cosine off of the right-hand side and give you sine divided by cos on the left-hand side. The good thing about that is that sine divided by cos is the same thing as tan. And after a little bit of rearranging, we can get it to a situation where we have tan is equal to -1 over root 3. So the next thing to do here is substitute, since our brackets aren't just x. That's going to give us tan of u is equal to -1 over root 3, and we're solving that from 0 to 4 pi. Now, you're not going to find the tan values exactly on the original unit circle, so I provided a tan version here, which is going to give us the angles 5 pi over 6 and 11 pi over 6. That's just for the first cycle. Don't forget that we're going from 0 to 4 pi, which just means we have to add 2 pi to our previous solutions. All we do from here is get everything back in terms of x, which means replacing u with 2x, which is what it originally was, and then dividing all of those answers by 2 to finally get everything back in terms of x. If you found this video helpful, then you should consider joining my free community. I host a Q&A call every week to personally help you through any of your specific questions, and you'll also get access to more resources like this, including written and recorded lecture content, as well as practice exams and SACs with detailed solutions. It's pretty cool, you should check it out. I'll see you there.